So we've presented the de Broglie hypothesis and made the case that matter exists as waves and even exhibits some behaviors that are unexpected when it comes to classical reasoning. But what we haven't really talked about is what do these waves really mean? How do we interpret these matter waves and make sense of what they actually mean? Okay, to help motivate this a little bit, let me draw a picture of the lowest eigenstate, or eigenfunction, if you will, of the particle in a box. Okay, it's a state that looks something like this. All right, it's essentially psi of 1 is equal to sine of pi x over L. Now, what exactly does this mean? Does it have a physical meaning? Well, if one is concerned about where the particle is in the box, does this wave function give us some notion about where it might reside? In other words, does this suggesting that the wave function might be more likely to reside in the middle than on the edges? Well, the answer to this is actually yes. The wave function is somehow related to where the particle is. But how is it related? Well, this is something that we can talk about in some length, but really what we do is we postulate that the wave function, if we take the square magnitude, is that it represents a probability density for finding the particle. So in other words, if we want to know the probability that the particle exists at some point x, we would calculate that probability by finding the wave function, taking its square magnitude dx, and that would represent, if you will, out of this continuous probability distribution, the probability that we would find a particle at that particular point x. Now, since we have a box in which the particles can't leak out, we have infinite walls on either side of this box, so we have an absolute certainty that the particle is inside the box. What does that mean? Well, it means if we integrate this quantity, this probability density, just between the limits of the box from 0 to L, and I'll specify that it's any of these particular eigenfunctions of the particle in a box system, the result of this must be equal to 1. In other words, the total probability of finding the particle anywhere in the box must be 1. It's got to be there or it isn't. Well, if we write this probability, if we write this wave function as equal to a times sine of n pi x over L, this a here is just a scaling factor. In other words, it does not have any real physical meaning for this wave function other than it scales this wave function up and down. So a would adjust this up and down, which means that it also adjusts the area under the curve, or the area that is represented by this integration. So what that tells us is that a becomes an adjustable parameter. And we can adjust that parameter to ensure that the total area under the wave function within the box is going to be equal to 1. So how does this work in practice? All right, let's go ahead and calculate what a must be for these wave functions. So if I take my integral from 0 to L of the particle in a box wave function squared, okay, that's going to be simply this prefactor squared times the function squared dx. And we know that that has to equal to 1. All right, so how can we deal with this integral? Well, this part here doesn't depend on x, so we can bring it outside the integral. So we have a squared outside the integral. And the rest of this, sine of n pi x over L squared dx, is the part that we have to deal with. Now, in order to work with this, we're going to introduce a trigonometric identity. And this may or may not be one you've seen before, but it's a pretty easy one to utilize. You may have seen that that the formula for cosine of 2 theta is equal to cosine squared theta minus sine squared theta. But you can also write it as 1 minus 2 sine squared theta. So what we want to do is we want to convert the sine squared theta here into a non-squared trigonometric function. So if I take this equation and solve for sine squared, what I would get is that sine squared theta is equal to 1/2 of 1 minus cosine 2 theta. So if I apply that trigonometric identity over here, I'll end up with, again, this part squared. I'll have a factor of 1/2 in front, so I'll go ahead and put that out front here. And then I'll have an integrand that is 1 minus cosine of twice this argument here. So it'll be 2 pi x over L dx. Okay, I can integrate cosine. In fact, the integral of cosine of ax is equal to 1 over a sine ax. Okay, so as I work that integral through, I'll find that this is 1/2 a squared times the integral 0 to L of 1 minus this, and actually instead of leaving the integral, let's go ahead and work the integral. The integral of 1 is just x, and the integral of this minus cosine 2ax is going to be minus 1 over a, so minus L over 2 pi sine of 2 pi x over L. And we're going to evaluate these from 0 to L. Okay, now this actually turns out to be pretty easy, because when I plug 0 in here, I get sine of 0. That's equal to 0. If I plug L in here, I'm going to have sine of 2 pi, which is basically an even multiple of pi, and that also is going to be 0. So in fact, what I find is that this term entirely drops out. It becomes 0. So the only part that's left is this term, and that's an easy one to evaluate. So I have x evaluated from 0 to L. That's just L. So I'll end up with 1/2 a times L. And that's equal to 1. So now I can solve for a squared. That's just equal to 2 over L. Or if I solve for a, it's going to be the square root of 2 over L. And one of the remarkable things here is that it does not depend upon n. It does not depend upon the particular eigenstate. So no matter which eigenstate I'm dealing with, I'm going to have as my adjustable parameter, I'm going to have 2 over L sine of n pi x over L. Now this adjustable parameter is sometimes also called the normalization constant, because it is the one value of a that causes the function to have this total area of 1 under the curve within its normal bounds. So this process of finding this normalization constant is called normalization of the wave function. And it's something that we'll always want to do, because when you have a normalized wave function, it makes other manipulations much easier. We don't have to keep dividing by the magnitude of the wave function.